Good morning, everyone. Welcome to yet another session on computational storage. My name is Vishwanath Maram from Samsung MSL, Director of Engineering. I'll be sharing the stage today with Professor Chang-Woo Min from Virginia Tech.
Yeah, I'm Chang-Woo Min from Virginia Tech.
So we both, MSL has collaborated with Virginia Tech on this particular use case, RETINA, exploring computational storage use case. So what we'll be covering on the agenda is industry trend, and then we'll go on the very brief on the computational storage, which will cover a 10,000 foot level SNIA CS API, which most of the working group has covered yesterday, along with Oscar covering in-depth on SNIA CS APIs, which is applied to Samsung SmartSSD. And then I'll hand over the presentation to Professor on the covering end-to-end framework for computational storage, which will go in depth of cross-layered RETINA key value store, along with dynamic composable RETINA computational pipeline. We just do a summary at the end and request for call to action. So I think most of you would have seen these crazy graphs on exponential data growth versus limited process scaling. This has been going on from last 15 to 20 years, or more than that, 3 decades graph, which shows that we are bounded by the CPU performance scaling. As we increase the number of devices on a particular server, we are bound to multiple factors, which were boiling down onto the CPU performance scaling. In spite of that, there is a lot of volume of data being exponentially grown. On this graph, if you see here, the left-hand side is in terms of zettabytes, and the x-axis is in terms of number of years. It is shown that by 2025, it will touch almost 180 zettabytes. As yesterday, one of the keynote speakers from Microsoft suggested, can we stop this data growth? No. It has to be increasing, and people have to keep on using on the social media. We cannot stop anything. Then how do we help the data growth by in a proper way with having full access to the analysis, analytics, and all that? So because of the data growth increase, we have a problem with the data gravity. The data gravity, how do we address this? Say, a lot of applications, and they request more performance and reduce latency. How are we going to address that? Let's take a simple application that would want to do a number crunching. Right now, in the current scenario, you take the data back to the host CPU into the DRAM, limited by the capacity of the DRAM, limited by the bound of PCIe bandwidth, and then you wait for the CPU to schedule your application, and then you crunch on the data, and then you get back the results. So you are bound to so many of the if and else conditions. Whereas here, even if you go to a hotel lobby, someone gives you a number by random number saying today is 25. How do you even interpret? Data is useless without any context. So how do we get that context? Then, if at all the lobby receptionist says that today is 25 degrees centigrade or 25 degrees Fahrenheit, as a human being, you know clearly it's going to be cold. You need to take an action of wearing a coat. That's the analysis you do when you know the exact context of the data. So that is what in this data gravity being seen as a problem. How can we attack this problem? The way to attack is introducing computational storage. Why don't we introduce compute near to the storage, by which you are trying to go out of these bounds, CPU bound, PCIe bandwidth bound, DRAM bound. But still, it is not a straightforward use case of computational storage for all the existing applications. You have to fine-tune your application or find out an application that goes well with the computational storage. So as part of that, here we are going to talk about a particular use case, RETINA, and then we go from here. So computational storage, as most of you heard a lot of terminology yesterday from computational storage. The lots of devices called computational storage drive, computational storage array, computational storage processor. During this talk, we are more discussing about a computational storage drive use case. And what is this computational storage drive? It is persistent data storage plus computational along with that. So here we are talking about Samsung SmartSSD with SSD with hardware acceleration engines. And then as part of this computational storage, standards have all come together, both SNIA and NVMe working group. They formulated NVMe computational working group along with SNIA technical working group with, on the NVMe side, TP4091 by having computational storage commands and TP4131 related to the memory. SNIA side, we have computational storage architecture and programming model, which is right now, computational storage architecture is in 1.0 with public review, and computational storage APIs is at 0.8 version of the spec. So at 10,000 foot level, I'll take you to the SNIA CS API library. What is this? It's a uniform interface for multiple configurations. APIs are provided in a common library. So if you see the diagram here on the right side of mine, here you are seeing a stack with storage applications, different adapters, and a SNIA CS API library. Below that, you will see plugins. These plugins will be the uniform interface for all, extensible interface for all these CSX to abstract CS interfaces. So below that, you are going through the regular NVMe driver, and then you talk to the CSX. So what are these CS APIs abstract? These are divided into various categories for discovery. If you regularly communicate with any NVMe controller, the first thing the PCIe bus does is PCIe enumeration by doing the device discovery. Either it could be PCIe Gen 3 or Gen 4, depending on how it negotiates the speed. In the similar fashion, you are doing a discovery of the computational storage devices here. It could be drives, array, or processors. That is the purpose of the device discovery APIs. And then we come to the device access. How do you access the device? Those are part of the device access. And then device memory. The memory could be either mapped or unmapped. It's an, I'll come to why we have resolved or discussed about mapped use case even before the standards have come in the next slide when we have introduced Samsung SmartSSD 1.0 version back in 2020. Near storage access. We need near storage access. As part of that, these APIs will help us, the near storage access APIs. And then copy device memory. You need an API to copy to and fro from the device. Download CSFs. I think you would have heard yesterday, computational storage functions. These are the functions that you are triggering for your applications. And then execute. Even if the hardware does not support any pre-downloaded or existing in the repository, a user can download the CSFs and then execute the CSFs. Device management. You need to know well how the device is performing. For that reason, you need these device management APIs. So how do we apply this computational storage using a simple application? If you see on the left-hand side here, you have the application, and you have a DRAM, CPU with SSD. It's a regular SSD. How do we apply that? Let's take an example where we want to do just an encrypted file. You want to decrypt it and use that file. Say, you have to read the data encrypted file to the DRAM. That happens in the step number 1. And then you have to trigger the CPU to act on it. And then CPU will be scheduled according to its availability. And then it will decrypt the file and give the application the results, end results. So essentially, you are going through the SSD, reading the data, putting it in the host DRAM, triggering the CPU, and then the application get the results. Now let's apply the same thing using computational storage. So queuing the request from the application, it will be the very first step. And then all you need to give is queue the input and let your computational storage device know that you want to act on a particular encryption function on the computational storage drive. What you are essentially doing in the step 2, you are just triggering the computational storage drive saying that you have the data at so-and-so address. Please use this address and data by giving this input to the compute function. The compute function will act on it, work on it, and give you the end data. Input does not get transferred into the host DRAM here. You are essentially avoiding the data to be transferred from the SSD to the host DRAM. You are reducing the CPU cycles by not waiting or by scheduling for the particular compute function, and you are reducing the PCIe bandwidth by not moving the data back to the host. So at the end, once the compute function acted upon it, you will get the end result to the application. So how are we on the Samsung Smart SSD here? So we are with the hardware logic for data-intensive operations such as image resizer, insert, lookup, database, scan, filter, etc. And it is more or less at-rest data processing. So the first generation of Samsung Smart SSD is more like FPGA interface-based Smart SSD. When I was talking about CS APIs, we were talking about the mapping of the memory. In the first generation Smart SSD, we have essentially put together a regular NVMe disk with an FPGA from Xilinx, Kintex. And what is essentially doing is we are mapping the FPGA to the host also, and that is why we are mapping the data bar memory from the Xilinx FPGA. So that is the memory that we use for transferring the data or working on it, which is commonly available in between the Xilinx FPGA and the NVMe SSD. So that is the first generation of the Samsung Smart SSD, which I was essentially talking to you as a PCIe switch, both NVMe SSD and a Xilinx FPGA in a single U.2 form factor. So the second generation Smart SSD, what is that we learned and how did we address these problems? So second generation Smart SSD, as you can see here, it is a standard compliant with NVMe TP4091. And we are trying to orchestrate a lot of these applications using this standards TP4091 and SNIA CS APIs. As part of that, here the second generation Smart SSD is more of industry compliant with the standard compliant, and it is in the form factor of E3.tel with PCIe Gen 4. And this also comes along with the Versal FPGA. So at this point of time, I'll hand over the presentation to Professor Changu Ummen. Thank you, Professor.
Thank you, Vish, for the nice introduction of the computational storage and its background. So I'm going to talk about the RETINA, which is our project designing the end-to-end framework for the computational storage. So before diving into the details of the RETINA, let's sit back and think about how we use and consume the data, right? So I wanted to present a very high-level idea of how we actually use the data. So first, we actually have to locate where the data is located, right? So that's the indexing step. And then after indexing is done, we should retrieve the data from some storage like a SSD or the hard disk drive. And then once the data is fetched, we should processing the data for our application, right? So typically the indexing and retrieval step has been done by the storage stack such as the file system or the key value storage engines, right? And then the computation, of course, that is a part of the application. For example, the TensorFlow will fetch the JPEG image and train the image classification neural network model. right? For example, the TensorFlow or the PyTorch, the deep learning training model, they'll essentially open the file, which is a part of the indexing step to locate where the data is located. And suppose that we wanted to train the cat image against the dog image, right? And then we will fetch the cat image by reading the data from the file system, just using the file system call. And then for this particular, the image training deep neural network model, it first requires some pre-processing steps. For example, JPEG image have to be decoded to the raw image, right? And then it should be resized, and then random crop and random mirror pre-processing operation have to be happen before feed into the GPU, right, for the model training. So conceptually speaking, the same thing happens. We can actually conceptually see the similar things happens for the database scan, filtering, and aggregation operations, such as, so this is a kind of a general model. So one of the big questions that I'd like to ask to ourselves when we actually start beginning this project is that how should the data pipeline should be redesigned when we actually having the computational storage device, right? So our answer is the RETINA, and under the RETINA, we actually have a slightly modified pipeline. The first one is of course, we should indexing step we have, so we should be able to locate where the data is, and then we have to fetch the data, right? But once the fetch the data, right, some of the operation, not all, some of the operation have to be done right after fetching the data, right? That should be executed on the computational storage side, and the rest of the operation can be done on any XPU, such as the CPU or the GPU. So RETINA basically covers the first three steps. So essentially, it conceptually consists of the key value storage engine plus computational pipeline on the computational storage device engines, right? So basically, in this talk, we wanted to propose RETINA, which is end-to-end framework for the computational storage. As I told you, RETINA consists of two parts. One is the data management part. Essentially, that's the key value storage engine. But here, we wanted to suggest cross-layered approach. Here, the cross-layered approach means that instead of just solely relying on the CPU or the accelerator on the smart computational storage side, we should use both, right? So that's the thing. And of course, the data management part, that's the key value store. So we should do everything that regular key value store have to do. So for example, we should provide some nice indexing algorithm to efficiently look up the data, right? And also we should provide some crash consistency. So the data should be protected from some random crash or the random file failure. Or the concurrency control also have been done by the key value storage engine. For example, if the multiple thread or process requests try to access the same data together, then the key value storage engine actually have to know that how to handle those concurrent requests. And the computational storage side, right? The RETINA provide at-rest data processing. So basically, we wanted to offload computation to the computational storage engine, and especially we wanted to change the compute functions as application requested on the fly. So from our perspective, the important thing is that the computation pipeline should be able to dynamically composable. So in the rest of the talk, I will first explain the data management part, and then move on to the computational storage part. So this is it. And then, this is the kind of the final design or from the user's perspective of the RETINA. So for example, instead of simply look up the cat0 to the JPEG, we are going to look up cat0 to the JPEG with some operations specified. So here in this case, we wanted to look up the cat0 to the JPEG, and then we wanted to perform JPEG decoding, resize, crop, and mirror operations. Then RETINA will look up the index and locate where the data is, and then perform the series of the operations specified by the users dynamically, and then feed the computed result to the GPU, right? So this kind of architecture has many advantages. One of the advantages is that we can actually exploit the fast internal peer-to-peer bandwidth inside the SmartSSD. So the data from the SSD to the FPGA memory under the SmartSSD can be fastly moved moved. That's the one advantage. Another one is that in many use cases, the pre-processed data, computed data is a lot smaller than the original data, right? For example, that is the very common to many deep learning, at least image classification applications. So in that case, that we can save a lot of the PCI bandwidth. Another one is that now, since we are able to dynamically compose the computation, so which basically means that we can share the computational storage device with multiple applications and multiple tenants, ideally, having a different computation request. So let's dive into the key value store part first. So as I told you, one of the key idea of the RETINA key value store is the cross-layered approach. So one of the reasons that we decide to choose the cross-layered approach is that there are something that CPU can do best, and there are something that FPGA can do best, right? If that's the case, why not use both, right? That's one of the key idea. So basically, we can actually by using the cross-layered approach, we can relieve the CPU from the data movement, so that basically we can reduce the power and bandwidth consumption. And also we can train the computation storage accelerator, here in this case, the FPGA, from the control plane operations, such as concurrent control and interaction with the operating system. That's a really difficult task to the FPGA, right? So we can actually reduce the complexity, right? So essentially, we use the CPU as a control plane. So CPU will take the role to communicate with the FPGA and the operating system. And also it will manage the concurrency and the caching algorithm. So all the control plane operations will be delegated to the CPU. And all the real computation operations will be delegated to the FPGA. So the FPGA inside the SmartSSD, we can actually leverage the high-speed interconnect between the FPGA and SmartSSD. And also we can offload the CPU-intensive compute operations to the FPGA. By doing that, we can actually reduce the data movement by bringing only the end result data to the CPU, right? So let me a little bit more explain why cross-layered approach is especially appropriate for the key value store design. And this is a kind of general conceptual diagram of the any sorted index, which is the key value store, which support the insert, lookup, scan, delete, update operations. So essentially, all the data will be stored to the data layer, what it called, and you can just imagine B+3 leaf node, right? So basically, each leaf node is nothing but just array of the key value pairs, and which store the actual data, right? And another layer is the intermediate layer, what we call the search layer. The load of the search layer is basically locate where the request data is located. So basically, the load of the search layer is that finding out what leaf node is likely to have the requested data. That's the basic role of the search layer, right? So suppose that we are trying to look up catcher to the JPEG, right? Then we will actually have to traverse the search layer and find out the location of the leaf node here, right? That is basically traversing the in-memory data structures, right? Essentially, which is a very branch divergent and also the branch divergent operation. So that's something that CPU can do best. And also, if you think about the leaf node operation, once the leaf node is located, what we actually have to do is that reading this information, leaf node to the memory, right? And then do some key comparison and find out catcher to the JPEG is what we want, and then return the result. So essentially, data array operation requires a data copy. So we can actually need to perform some form of the parallel key comparison. That's something that this FPGA can do better, right? So that's the thing. And then, so with having this in mind, how we realized this idea in the computational storage, especially the SmartSSD, of course, we're going to put the data layer to the SmartSSD. Essentially, that will be stored to the SSD part of the SmartSSD. And then besides the SSD, we were going to have the accelerator. In case of SmartSSD Gen 1, we will have FPGA. and Xilinx FPGA. FPGA have a global memory named Common Memory Area, or the CMA. CMA is the kind of memory area that SSD can directly perform the peer-to-peer data copy from the SSD to the CMA memory area. And also CMA memory area is the PCIe bar address, so the CPU can directly see the CMA memory area. So yeah, search layer will be basically, in our design, search layer will be stored on the host DRAM, CPU, on the Xeon side, and then manipulated by the host CPU code, and the data layer operations like manipulating or look up the key and values within one B+3 node will be performed by the FPGA on the SmartSSD. Right? So basically, this way we can use the host CPU as a control plane, basically triggering the FPGA kernel and SSD I/O and concurrency control. And we use the FPGA as the address data processing engine, manipulating and handling data on SSD. Right? So let me give an example how actually these ideas are realized in the with an example. Suppose that we wanted to look up cat02.jpg. And then the first hosts actually have to traverse the intermediate node of the tree to locate where the leaf node, to appropriate leaf node, right? And then the host will trigger the SSD I/O, right, of the leaf node that actually triggering the copy of the leaf node to the CMA memory region using the peer-to-peer operation. Then host will again trigger the lookup operation, lookup kernel inside the kernel. So as I told you, the data layer will be processed by the FPGA. So each data layer operation, such as a lookup within a B+3 node, and or insert or update or scan against the B+ node will be handled by the FPGA kernel. So the FPGA lookup kernel will be triggered by the host CPU. Then the lookup kernel will find out cat02.jpg is what the user want, and the final result will be copied to the CMA memory region. And since the CMA memory region is the PCIe bar address, so the CPU can actually fetch the data. So that's basically how RETINA key value store works, right? So besides this, there are a lot of the details that I didn't explain because how to perform the insert operations or the scan operations, and also how to add a cache design or how to efficiently guarantee the cache consistency, and to avoid losing the data under the sudden power failure, or how to perform the efficiently control the concurrent operations. But this is the overall idea of the RETINA key value store. And then let's switch the gears and let me move on to the RETINA computational pipeline. So let me first explain what is the computational pipeline. So the computational pipeline is one of the parallel computation model. So idea is basically we get the input and then we will perform series of the operations in a pipeline manner like what CPU does, and then we'll find out the result. And computational pipeline is of course consists of compute kernels. And one of the nice things of the computational pipeline model is that it'll only interact, all the inputs will coming from the input stream, and all the output will spit out to the output stream. The stream is nothing but conceptually nothing but just a fixed size ring buffer conceptually. So why this straightforward model is very beneficial in my view, is that the model is very simple and well-defined interface. Computation kernel only interact with input kernel and output kernel. So that's very easy. And actually that brings another very interesting aspect, because since computation kernel is only interacting with input and output stream, so we can actually easily integrate different types of the kernels. For example, some kernels can be implemented using the OpenCL, and some kernels can be implemented using the SQL, another can be using the low-level RTL, but as long as they are just follow the input stream and the output stream model, they can actually integrate very easily. And another one is that this is basically the same as the CPU pipelining model. So basically that means that we can actually naturally exploit the pipeline parallelism. So we can actually easily increase the throughput. So in this case, that we have the 4 stages of the pipeline. This 4 stages of the pipeline can handle the 4 different images at the same time. So which is a pretty nice property. So another important thing that we wanted to achieve is that we wanted to achieve the pipeline as a dynamic composable, because the hardwired pipeline are very not generic enough. That's the very specific to the one type of the application. So, and also the applications may require different compute kernels or different orders of the same compute kernels for their purpose. For example, the JPEG decoding can be used for, not only used for the machine learning image classification training, or JPEG decoding can be used for the Photoshop style image manipulation applications. And also, if we have a dynamic composability, basically that means that the compute kernel is the unit of the reusable code, right? So that actually allows us that the multiple applications and ideally multiple tenants can share the same computational storage. So then our main design question is how to achieve dynamic composability, right? So eventually what we wanted to have is that dynamically composed compute kernel as per user request on the fly. So our approach basically is the central pipeline manager, what we call arbiter-based approach. Basically, essentially, there are some assumptions. So we have compute kernels, and in this particular work and our particular implementation, we just assume that compute kernels are already somehow installed, downloaded on the FPGA. And of course, as we discussed, compute kernels only communicate through the streams, right? And they do not communicate directly each other, like a hardwired pipeline architecture. But with a centralized pipeline architecture, each kernel actually communicates from 2 streams with a centralized pipeline manager, which is the arbiter, right? And arbiter is basically the resource scheduler, so it'll actually have to schedule the order of the execution, which compute kernel should be executed, and how the FPGA memory should be managed, right? So let me give a little more concrete example how RETINA computational pipeline architecture will work. So in this example, these are the computational pipeline we have. For example, we have lookup and insert kernel, which is necessary for the key value store operation, and JPEG or the PNG decoding operations, and also resize, crop and mirror operations are also one of the pipelines. They all connect to the arbiter kernel, which is another FPGA kernel implemented using the FPGA logic. And they are all communicate through the input and output stream. And then if the user send a request to the arbiter, let's say I wanted to perform the lookup first, and then wanted to perform JPEG decoding, resize, crop and mirror operations. Then arbiter will actually perform the series of the operations. And one thing that I really like to note is that copying the entire JPEG image over the stream will just waste of the memory bandwidth, right? And the memory itself. So we actually just hand over the pointer to the CMA memory region. So the actual amount of data passed through the CMA is passed through the stream is very small. And as I told you, the lookup and insert kernel, those kernels are also necessary for the RETINA key value store operation. But from our computational pipeline point of view, that's just one of the kernels, right? So let me give an example how actual RETINA computational pipeline works. And here the example is that we wanted to look up the cat 0 to the JPEG, and we wanted to perform JPEG decode, resize, crop and mirror operations. So the host will first look up the search layer, right? So it'll actually perform the lookup, the search layer, and find out where the B+3 leaf node is located. And then we'll perform the SSD I/O. So the SSD data on the SSD will be copied to the CMA memory region on the FPGA side, right? And then the host will send the request to the arbiter, right? And the request will be lookup, JPEG decode, resize, crop and mirror operation. Then arbiter will receive the request from the host, and it will first perform the lookup operation, right? And then after finish the lookup operation, we will get the cat image here, original cat image here. Then arbiter, they will keep forwarding the request, following the original user request, right? Then we will actually have a final, pre-processed cat image, right? So besides this, this is the high-level idea and overview of how the RETINA computational pipeline works. And I did not explain how computational pipeline can be integrated with the update, insert, scan operations, and also how the arbiter actually have to perform the scheduling or manage the memory management and how to exploit the pipeline parallelism. But those things are not explained, but these are the high-level idea of the RETINA computational pipeline. So we actually implement the RETINA computational key-value store in the pipeline with the SmartSSD Gen 1, initially with the Xilinx OpenCL API. And we actually ran the popular YCSB key-value storage workload. And YCSB key-value storage workload is the kind of standard benchmark to evaluate the key-value storage performance. And here in this example, we just run the YCSB key-value storage workload without any compute kernels. And from our point of view, this is the worst case performance because that essentially RETINA is for the offloading the computation efficiently, right? But we just ran the benchmark without computation kernel, so this is just the worst case performance. And we actually, to see how RETINA performs well or the bad, we just compare the performance with the RocksDB. And YCS benchmark have YCSB ABC and a couple of others sub-benchmark, which has different read and write ratios. As you can see here, right, for the YCSB-C workload, which is 100% lookup workload, RETINA actually outperforms the RocksDB, right? And also the YCSB-C, that's also the same case. And also the CPU utilization is much lower than the original RocksDB. But as you can see here, the RETINA performs a little bit worse than the RocksDB, but we're going to explain a little bit later in the next slide why it is and how we can actually improve this, right? And then we are currently working on the RETINA again, using and porting our initial OpenCL implementation to the SNIA CS API implementation with the SmartSSD Gen 2. And we are expecting that we will get a higher performance with SNIA CS API and SmartSSD Gen 2. One of the main reasons that why our YCSB-A performance is worse than the RocksDB is that the YCSB-A has 50% of the update operation. That basically means that we actually first perform the lookup operation, and then B plus leaf node will be copied to the CMA memory region. Then our update kernel will update data on the CMA memory, and then that modified data actually have to be written back to the SSD. And here, the first generation of SmartSSD and the OpenCL API, that write back operation to the SSD should be triggered by the CPU. So it requires additional interactions between the FPGA to the CPU that actually add the latencies. That's one of the main reasons that our update performance is slower. But if we are leveraging the CS API and SmartSSD Gen 2, we are expecting that we are improving the performance by reducing that additional interactions between the FPGA and the CPU. Okay, that's my part. And
okay. Thank you, Professor. As a summary, what we have tackled here is the challenges of exponential data growth and limited process scaling by using computational storage APIs, which is a standardized version of SNIA CS APIs, and then Samsung Smart SSD, which are available both as Gen 1 and Gen 2. And here we spoke in terms of RETINA end-to-end framework for computational storage, which is a use case for computational storage. And as an ecosystem development, this will be the first use case which we have tackled outside of Samsung as a cross-layered key-value store for data management and dynamically composable computational pipeline as an end-to-end application given with the SNIA standard APIs and TP4091 command set with the computational storage Gen 2. And we expect more performance as we have explained in the previous slide. We are expecting better performance with the Gen 2. And with that said, we have call for action. We have a couple of other sessions followed by today in the computational storage track from Samsung. Also, yesterday there was a keynote presentation from Dr. Yangsaki, along with a presentation from Oscar on CS APIs, followed by multiple presentations from the SNIA community and technical working group community. We request to help us build the ecosystem, join us in the standardization efforts. Last but not the least, I would like to say thanks to NVMe and SNIA working groups for finding that there is an importance in computational storage and creating the working groups and working on the standards. Thank you.